recording works again. Okay, so the plan for today is talking about GFS. I'm going to do it in sort of multiple steps. One, I'm going to talk a little bit about storage in general and why it's so important, and why we'll spend a lot of time in this class talking about it. Then I'm going to talk a little bit about sort of intro to GFS and its main design. We'll focus on consistency, which will be sort of the main theme through this lecture. And as part of the consistency, we probably do hopefully there's still time, do a breakout room and talk a little bit about, in the breakout rooms, about the lecture, the question that was posed for lecture, and then we'll resume discussion of consistency. Okay, so I'm going to talk a little bit about storage systems in general and why they feature so prominently in 6824. And the main reason is it is just a fantastic building block for fault-tolerant systems. And so the basic idea is that if you can make if you can build a durable storage system, then you can structure sort of your application as the app is basically stateless, and then the storage holds all the persistent state, and that simplifies the design of the app tremendously, because the app basically doesn't really have any stable storage, that it has to maintain itself. In fact, sort of factored it all out to the storage system. And so you can start up a new application very quickly. It crashed, doesn't really matter because it only has soft state, not any hard state. And you start it up again, and then once you start it up again, you just reach the state from the distributed storage system. And you can see this, correct? Like when you look at any website, basically they're structured in that way. Like there's a storage backend, that maintains the state, and then there's sort of the application middle tier that does the application-specific computation or whatever, runs JavaScript, Go, or whatever, and it front ends that out, to clients on the internet. And so storage is just like this fantastic building block. And I think this is one reason that we're going to see this over and over in this class. That means that the storage system itself, of course, has to be highly fault tolerant. And that turns out to be a very tricky thing to do. And so that is the other side, the flip side of it. We make life for the application easy, but the designing an actually fault tolerant system, storage system, is not easy. And so why is it hard? And basically come down to one reason that drives these designs, which is like we generally want high performance. And you think about the storage system for today, GFS, its main goal is to basically support MapReduce types applications, and so it really needs high performance. Well, what does that mean? Well, it means that you typically have to shard data across servers. So you can't use one server, you have to use multiple servers. And the reason you want to read from the disk, often a particular machine has a limited throughput. If you want to read more than actually a single disk can sustain, you have to use multiple disks, and you have to use multiple network cards. And so you can immediately get into this sort of large-scale systems, as in the GFS papers, where you have thousands of machines. But if you have many servers, some are going to fail. And you're going to get failures. Or maybe you just can say it more explicitly, you have constant faults. And let's assume that a computer crashes once a year. Now let's say you have 1,000 machines, like in the GFS paper, or actually many more than 1,000 machines, but a minimum of 1,000 machines. How many failures are you going to see per day, roughly?
Around 3.
Yeah, around 3, right? But that means that the sort of a failure of a computer, like my laptop at the beginning of the lecture, is just a common scenario. And so if you're going to move up to more than 1,000 machines, 10,000 machines, 100,000 machines, and you run the application that uses that kind of number of computers, you're going to get faults. And so that means you want a fault-tolerant design. And to get fault tolerance, at least in the case with the storage system, the typical approach, the way to go is go with replication. Copy the data on multiple disks, so that if one disk fails, the other disk hopefully have the data. But if you go into replication, and so the data is in multiple places, that runs into the challenge that the data may be out of sync, and so you can actually get into potential inconsistencies. To avoid these inconsistencies, if you desire strong consistency, basically your replicated system behaves as if it's it has the same behavior as an unreplicated system. Then you will need some consistency protocol, and that requires some maybe sending messages, and that may lower performance. And maybe the messages themselves is not a really huge performance overhead, but typical, as we'll see, you might actually have to read or write to durable storage as part of that protocol. And reading and writing to storage internally tends to be quite expensive. And so here we see this conundrum, like we want high performance, we want fault tolerance because we have many servers. We want high performance, so we want many servers. We have many servers, we mean fault tolerance. That means replication. That means inconsistencies. Because you have data in multiple places, to fix the inconsistencies, we need a sophisticated protocol that might lower performance. And so here's this fundamental challenge, in designing these distributed storage systems, that there's a struggle between consistency and basically performance, and we'll see that throughout the term. So let me talk a little bit about consistency. At a very high level. And I'll promise you for the rest of the semester, we're going to go in more detail as we go. So first, let's talk again about the ideal consistency. In ideal consistency, the simplest way to think about it is that basically the machine behaves as if it's a single system. That's the desired behavior. And there's two things that make that desired behavior, or two hazards that make that desired behavior hard to achieve, or at least it requires some thinking. And one is concurrency, and second thing is failures. So let me start with concurrency, because even if you have a single machine with multiple clients, so you have concurrency within the single machine, you actually have to think about consistency. This of course is quite obvious. Let's say we have one machine with one disk, multiple requests come in from different clients. And if the machine is a multiprocessing machine, they might actually run these requests truly in parallel. So let's think a little bit about it. What does it mean? So let's say we have on client one that does a write operation to a key X, and it writes 1. And at the same time, there's a request coming in that writes to X2, but actually writes the value 2. Right, and now if we want to specify or state what consistency means, we need some rule about what will happen. And the rule is typically phrased from the perspective of the reader. So let's say there's another reader coming in, or another request coming in from another client, and it actually reads X. And the question is what is the value that actually that reader or that this client observes? And a little bit more complicated or more interesting, let's say we have a fourth client, which we're going to bring out this issue of consistency definitions more clearly, and it also does a read of X well after the client 3 actually read X. And so now we have to state what is the desired outcomes and what are incorrect outcomes, and that's really what defines consistency. So let's take the first case, C3. What would be a reasonable outcome for the read of C? What is a reasonable outcome for the read of C3 to return? What values? What value would make you happy or make an application programmer happy?
2.
2 would be very reasonable. Any other reasonable values?
1.
Yeah, 1 would be reasonable. Right, because the operation happened concurrently, so maybe we don't really know which one. We don't really want to restrict in what particular order they go. So we can say either one is fine, because they're running concurrently. What are some values that we would like not to see? for the C3 read?
7.
Yeah, 7. Any other value, right? Because nobody wrote that, so that would be undesirable. Okay, so good. So like we agree that probably just the reasonable outcome for C3 would be either 1 or 2. Okay, how about C4?
The same as C3.
Really? Exactly the same? So let's say C3 returned 1. What do we expect C4 to return?
Whatever C3 saw.
Yeah, because it ran well after C3, right? So if 1 was returned, we expect 1 here too, right? If 2 was returned, we expect 2 here. Does that make sense? Okay, so there's like a super brief, sort of introduction of sort of saying like, how can you define consistency? And then the typical way we do it is using sort of traces, and we argue about like what are correctness, for particular traces, and we'll see more of that. And of course, the server can enforce, this kind of consistency by, for example, using locks, as you have done as you do in the MapReduce or in sort of any concurrent Go program that you write. So that's sort of the standard technique, to enforce consistency in terms of in the presence of concurrency is to use locks. Now, in a distributed system, the ideal consistency, sort of, as I said, there are 2 hazards, and the second hazard is basically failure. So just replication in general. Like we have 2 servers now suddenly. So here's S1, here's S2, and both have a disk. And we have our same clients as before, C1 and C2, and they write to X. And let's say just to illustrate like what kind of complications, what kind of just to illustrate that we actually have to do something. Let's start with like the most dumb replication plan. So like very bad replication plan. So in this particular bad replication plan, what we're going to do is like, we're going to allow a client, when a client actually wants to update or write, we're going to tell it to basically, the protocol that we're going to follow is the client writes it to both servers in, whatever. Don't really coordinate that, it just writes it to both. And so, for example, if we have client 1 and client 2 running, then, maybe client 2 does the same thing. And then we're also going to ask ourselves the same question, like, what does C3 see when it actually reads? And let's assume that for reading, we're going to say like, we're either way. We're going to read from either replica. As I said, this is a very bad replication plan. Basically, there's no restrictions. So what are the possible outcomes? So this guy writes 1, this guy writes 2, and now we see 3. What are the possible outcomes for each read?
1 and 2 again.
Yeah, 1 and 2. No, nothing really that bad happening, correct? How about C4? We do a read of X, well after C3 X, like as in the previous board.
Also 1 and 2.
Yeah, 1 and 2 again. But what happens if C3 reads 1? What does C4 may return?
1 or 2.
1 or 2. And is that what we want or not?
No.
No, I mean, again, correct, it'd be difficult for an application writer to actually reason about this. Particularly even if C3 and C4 were the same thing. You first read to a teacher 1, no modification made, and the next second read returns another value. How is that possible? It makes application programmers difficult to write. And so, and the reason, of course, that this inconsistency shows up here is because we basically have no protocol, to coordinate, the clients, the readers, and the writers. So we need some form in the distributed system. Typically, we need some form of a protocol to fix these, to get the desired, to enforce that we get the desired consistency. Okay. And so what we're going to see in the rest of the semester is a whole bunch of different types of protocols that have different trade-offs in terms of the fault tolerance and the consistency. Okay. And in fact, to sort of get our get our head in that kind of thinking, we're going to use a whole bunch of different case studies. And the case study for today is GFS. And this is an interesting case study, otherwise we wouldn't have signed it. And one reason it's an interesting case study because it brings out sort of all these, sort of these core issues. Right? GFS, is designed to get high performance. That means it actually uses replication and fault tolerance. It struggles with this consistency. So it's like the 3 or 4 sort of themes that we're going to be consistently seeing throughout the semester, show up in this one paper. The other side of this why is an interesting case study because it's a successful system. Google doesn't actually use GFS, at least at this point, is my understanding. There's a successor file system called Colossus, but it's inspired by GFS. But there are other sort of these cluster-based file systems, for like MapReduce type of use jobs like HDFS. They're also very much inspired by the design of GFS. One thing that is actually interesting at the point that this paper was written in the sort of late early 2000s, it was pretty, distributed file systems were well understood topics. So people knew about fault tolerance, people knew about replication, people knew about consistency, all that kind of stuff was sort of pretty well understood. However, nobody actually sort of built a system at the scale of thousands of computers, and that sort of brings out a number of challenges that previous systems have to not address. And in fact, the design is not completely standard. So the end design that we're reading about is not was not sort of the standard design that you would see in academic papers at that time. And there were sort of 2 aspects that make it non-standard, both of which we'll we'll spend more time on. One is, there's actually a single master. So the master is not replicated. There's a single machine that is sort of in charge of like almost all the coordination in the system. And that is unusual. Why would you build this fault tolerance system which has a single point of failure? Right? That would be sort of not something that people in the academic literature were doing at that time. And the second thing is that it's not consistent. It can have inconsistencies. And again, mostly in the literature at that particular time, people were really sweating actually, to build, distributed systems that actually have strong consistency and, don't have the anomalies that, we saw on the previous board. And so even though like a lot of the core techniques, were well known, the way they were putting together was actually quite different. And so that makes it interesting, and particularly, the scale, which this system actually operates is impressive, and pretty common even for today. So this issue of struggle between fault tolerance, replication, performance, and consistency is a standard problem, a recurring problem for almost any distributed storage systems that people build today. And changes over time. So like S3 for a while, didn't really have to have that strong consistency. Lately it's gotten much stronger consistency. Okay, so I want to, since the paper is really driven and the design is driven by by performance, I wanted to go back to the MapReduce paper for a second. And this is a graph, of the MapReduce paper. And one way to think about GFS is that it's the file system for MapReduce. So the goal is to actually run many MapReduce jobs and get high performance. And we know that basically we can tell from the MapReduce paper already that sort of GFS is impressive in that manner in terms of performance. So if you look at the this side of this graph, this is straight out of the MapReduce paper. This is the normal execution of one of the MapReduce jobs, and it has 3 sort of parts to it. One is the first part is input, like reading the input files, the input to the mappers from the file system. And in case the paper didn't say much about it, but those are read from GFS. There's the internal shuffle that we don't really care about, and then at the end, the reduced jobs write back the results into GFS, and so. The performance, part of the performance of these MapReduce tasks is determined by the rate at which the mappers can actually read, data from the GFS file system, right? So we have running many, many mappers at the same time. In fact, some mappers from different jobs, may be reading the same files. So we look at the input, like this top, graph shows the input in terms of megabytes per second at the rate at which, the mappers actually jointly, collectively for one particular job, can read from the file system. And as you can see, it goes over well over 1,000 or 10,000 megabytes per second. And the first question to ask you is maybe like, is that an impressive number? Yeah, should we be impressed with that number, or are we thinking, well, give me one disk and I do it too? Anybody?
I think because it's older, maybe yes.
Okay, good. So what is for SSD? How much? What rates can you read? Okay, let me tell you this. Roughly the throughput of a single disk at the time that for this paper, it was around like 30 megabytes per second, like somewhere in the tens of megabytes per second. So here we're looking at, well over 10,000 megabytes per second. Correct, and so that is an impressive number. And you have to do work. That's we'll see in the GFS design that allows that kind of throughput. And of course, if the disk technology, in the case of the GFS, of course, if the disk technology was faster, it would be, what the real goal here, correct, is like we have 1,000 machines, maybe each one has a disk, each one can read at 30 megabytes per second. We just want 1,000 times 30 megabytes per second to get out of it. Okay. And so that's sort of what drives a lot of this design, is to basically allow these mappers to read in parallel from the file system, from this joint file system. Okay. So let me say a little bit more about this. So like, what are the key properties that GFS has? One, big, large data set. With that, I mean that. And so, the data set you should think about is like the MapReduce data sets. So for example, presumably the whole the complete crawl of the World Wide Web is stored in this distributed file system. Has to be fast, as we talked about. And the way they get like high performance is sort of doing automatic sharding. Shard the files across multiple disks, allow multiple clients to read from those disks in parallel. All right. Another goal is global. And what that mean, it's shared, or all apps see same file system. And that's convenient, right? Like if you have multiple MapReduce jobs, that operate on the same set of files, they can first of all read all the same set of files, but they can produce new files, and then other MapReduce can use those files again. And so it's a very convenient, it allows sharing between applications. So it's very convenient to have. And of course, GFS has to be fault tolerant. It's likely there are going to be failures, and so we want like automatic, close to automatic fault tolerance as possible. And we'll see GFS doesn't provide complete automatic, but does a pretty good job of actually getting good fault tolerance. Okay, any questions about this part so far? Like a broad intro to this topic, and sort of a few intro words about GFS. Okay, let's then talk about the design. So here's the design is seen in from the figure 1, I think, in the paper. And there's a couple of things I wanted to point out and talk a little bit more in detail about. So first of all, we have an application, and that the application again might be MapReduce job, consisting of multiple reduce tasks, multiple map tasks, and they link with the GFS library. And so it's not a Linux file system. This is not the file system you use to whatever edit your files on or compile. It is really intended as a special purpose file system for these large computations. And as I said before, our real goal, correct, is that achieve that impressive number. Or like, we want the number of megabytes, from a single disk times the number of machines, and a single application should be able to exploit that. And so the way they arrange that is to have a master that is basically in charge of actually knowing where things are. And the client just periodically, talks to the master to retrieve information. So, for example, it opens a file, and the open call will result in a message, to the master, and the master will respond back and say, like, for this particular file name, the chunks that you need are here, or these are the chunks that you need. And there's called chunk handles, there's identifiers for the particular chunks that constitute a file. And here are the servers that serve that chunk. So you get back, a chunk handle, as well as, a bunch of chunk locations. And one file might, basically a file consists, if you think about a big file, it consists of many, many chunks. Chunk 0, chunk 1, chunk 2, etc. Chunk 3, blah, 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 etc., etc., etc. And each chunk is pretty big, like 64 megabytes. Right, so even an application wants to read, the second 64 megabyte, goes to the GFS and says, like, hey, I want to read, the second chunk, of this particular file, and then the GFS answers back with the handle for, chunk 1, as well as the servers that actually holds chunk 1. Right. And so, multiple applications might ask, for chunks from the same file. And they will get, for example, the one application might be reading chunk 0, another application might be already at chunk 2. They will get different lists back for each of these chunks. So then the GFS client, once it knows the chunks and chunk locations, and basically straight talks to the chunk servers. And basically read, the data, at the speed of the network, and maybe whatever disk, that sits behind this particular chunk server. Directly to the application. And here you can see where we're going to get the big win, right? Because we're going to be able to read, for multiple, multiple clients can be reading from multiple disks at the same time, and we're going to get like tremendous amount of performance. Right? So, for example, if like here's a map task running, here's another map task running that also is a client. They're all going to be talking to this set of servers, that hold, the chunks of all the collection, the data set. And those are going to read in parallel from all those different chunk servers. And that's going to give us like the high throughput number. Does that make sense? Is that sort of the overall plan clear here? Just to sort of complete it, like a chunk server is nothing really else than sort of a Linux box, Linux computer with disk to it. And in fact, the 64 megabyte chunk is just stored as a Linux file in the Linux file system. Okay. Okay, so I want to zoom in on the different pieces, and I will start with the master, because masters are really the control center here. So we'll talk a little bit about the state that actually the master maintains. Okay. So first of all, it has the mapping from file name to an array of chunk handles. And as you saw in the paper, one of the goals of actually is to maintain all this memory, most of the information actually directly available in memory, so that the master can respond to clients very quickly. And the main reason to do that is because there's one master, many clients. You want to execute every client operation as efficient as possible, so that you can scale the master to at least a reasonable number of clients. And then for every chunk handle, the master maintains some additional number information. In particular, it maintains a version number. And a list of chunk servers that hold a copy of that chunk. And as we'll see in a second, one of them is named, one of those servers is a primary, and the other ones are the secondaries. And the typical number that, a chunk is stored at is at 3 servers. We can maybe talk a little bit later about like why 3. And then, there is a lease associated with each primary. So there's a lease time maintained as well. Then there's two sort of other big, sort of storage components, and these are sort of the the file system level things. And then in terms of implementation, there's a log, and there are checkpoints. And since the master is sort of the crucial, the control center, whenever there's a change, to the namespace, for example, you create a new file in GFS, or the mapping from file name to chunk blocks changes, all those operations are written to this log, and the log sits on on stable storage. And the basic idea is that before responding to the client that the change actually has been named, the master writes it to stable storage first, and then responds to the client. And so this means that if the master fails or crashes, then later comes back up, it can replay the log to reconstruct, the state of its internal state. And by writing it first to storage before responding to the client will never observe strange results. You could do it the other way around, correct? And that will result in a problem because the client will think that the file has been created, server crash, it comes back up, and then the file doesn't exist. So there's sort of another consistency point. Now, replaying always back all the operations from the beginning of time from the log is, of course, undesirable. That means that if the master crashes and we have only one of them, will be down for a long time. And so in addition to that, it actually keeps checkpoints in stable storage. So periodically, the master makes a checkpoint of its internal state and the mapping for file name to array chunk handles, and stores that on stable storage. And so then it only has to replay the last part of, basically all the operations in the log after the last checkpoint. And so the recovery is actually quicker. So there's another couple of interesting questions that we can ask ourselves, like what state does need to end up in stable storage, for the master to actually function correctly. And so the first question to ask is, how about this array of chunk handles, the mapping from file name to chunk handles? Does that need to be stably stored? Or can it be only memory?
But if the master crashes, then I think it can get that information from the servers, chunk servers. So maybe only main memory.
Yeah, well, that's an interesting question. What do other people think?
So it can be reconstructed from the log. So when the server crashes, only the log needs to be in the hard storage, and then it can reload it from the log to main memory.
Yeah, so it definitely has to be in the log, correct? So we agree that this array of check handles basically has to be in stable storage. Because otherwise we lose, like when we create a file and we didn't write it to stable storage, we just lose the file, right? And so this mapping from file name to chunk handles needs to be in a stable storage. How about this chunk handle to list of chunk for servers? Does that actually need to be in the log?
I think in the paper they say that when the master reboots, it asks the servers to tell the master what the chunks that they have are.
Yeah, correct. So this is not actually, this is basically just volatile state, not stable storage. So, and the same is presumably true of the primaries and the secondaries, and true of the lease time. How about the version number? Does the master need to remember on stable storage the version number or not?
Yes, because it needs to know if the chunks in the other servers are stale or not.
Yeah, exactly. That's exactly right. Correct. So the master must remember the version number, because if it doesn't, and like the whole system went down, and the chunk servers came back up, and maybe the chunk server actually with the most recent data does not come up, like an older guy comes up with like version number 14, then the master has to be able to tell that that chunk server with version number 14 was not the most recent chunk server. And so it needs to maintain, the version number on disk so that it actually can tell which chunk server actually have the most up-to-date information and which ones don't. Okay.
I have a question here.
Yeah.
If the monster fails and then it has to come up, it's anyway going to connect to all of the chunk servers and it will find out what the largest version is of
Yeah.
any chunk server, right?
Will it find out what the last, first of all, it will try to talk to all chunk servers, right? And some chunk servers might be down.
Okay, yeah.
And that may be just the chunk server that actually has the most recent version, right?
Yeah, okay.
So you can't take the max of the live chunk servers. That would be incorrect. Any other questions about this? Okay, let's look at the two sort of basic operations to really get down to consistency. And of course, that's going to be reading and writing. So reading a file, and then we'll talk about writing a file. So reading a file in some sense is straightforward. We talked about it. Basically, the client sends a message to with the file name plus offset to the master, and basically ask, please give me, the chunk servers and the chunk handle that that hold that data at that offset. And so an end finds the chunk handle. So if I like a read byte, whatever, 0, it's pretty clear, correct? That has to be the first entry in the list, from file name to chunk handle. So the master finds the chunk handle and basically replies, with the master replies to the client with, the chunk handle and list of chunk servers for that handle and the version number. So basically, the client gets back a message saying, that's chunk, 221. And here are the free machines or the IP address with the free machines that actually have it. And the version number is like version number 10. Then the client caches this list. And then it basically sends a message to the closest. So reads from closest server. And so why does the client actually read cache this information? As we see later, correct, that actually causes some problems.
So it doesn't have to contact the master for some time if it wants to read again or write to that chunk.
Yeah, and why is that important?
To reduce the traffic.
Yeah.
And in general, it takes less time if you have less communication with the master.
Yeah, and then the salient aspect, correct, of this design is that the master actually is a single machine. And a single machine can just have a limited amount of memory and a limited network interface. And so if you have too many clients talking to it, it wouldn't be able to serve, right? And so client caching is important to reduce the load on this single machine. Okay, why read from the closest server?
Minimize network traffic.
Yeah, minimize network traffic. So the whole goal, correct, is to pump as much data to the client as possible at the highest throughput. And we have to there's two problems if we have to cross the data center network. One, there's probably some topology, and we may be swamped like the top links of that topology, and it may actually increase latency, to actually get to the other site. All right, so it's important to be able to read to the closest site again to basically maximize the throughput that a joint set of clients can sort of experience when they're reading in parallel from many chunk servers. Okay, so the chunk server S basically checks the version number, and if the version number is okay, then send data. Okay, and why is the check of the version number there?
to check if it's too stale.
Yeah, we usually do our utmost best to avoid reading stale data. And as we'll see in a second, we don't do, GFS doesn't do a perfect job at, but tried hard to minimize, the occurrences of clients reading stale data. Okay, that's reading, reasonable straightforward. So let's look at writing. So this is the picture from the paper. And so let's say a client wants to, let's focus on append. And so they argue that a very common operation for them is to append a record to a file. And can we see why, given what you guys know from sort of MapReduce and Google, does that make sense that why append is so important?
Because largely in doing MapReduce, you need to, or as the map function spits out information, it's largely just adding on information rather than changing previously spit out informations.
Yeah, maybe the map is not the best example because it writes it to the local file system, not to GFS, but the reducer does. The same argument holds for the reducer. Yeah, so the workloads they're writing is basically consume a lot of information and append records to a file with the resulting computation, with the result of the computation. Okay, good. So step one, we have a client. It will talk to the master to figure out like where to write to. And so the master looks in its table, right, the file name to chunk handles. And finds the chunk handles, and then looks at this table of chunk handles to servers to find the list of servers that it has that have a particular thing, that have that particular chunk. Okay, so what happens next? So there's two cases, right? Like when there is already a primary, and the second case, the first case, well, the two cases, having a primary or not a primary. So let's say this is the very first time that this particular client contacts the master for this particular chunk. Nobody else has done it so far, so there's no primary. So in that case, we need to, the master needs to pick a primary, right? How does it do that?
I think the master just picks any of the available chunk servers, right?
Yep. Yeah, picks one. So it picks one of those are primary, and the other ones are the secondary. What other steps are involved in this sort of?
Yeah, and then subsequently the master grants a lease to that primary, and that lease has a certain date of expiry.
Yeah, what else does it have? There's one more other piece of crucial information. Even
it increments the version number.
Yeah, it increments the version number.
Oh, oops.
Yeah, step one is increment the version number, correct? Because you're going to make a new primary, and whenever time you make a new primary, you go sort of like one way to think about it is like a new epoch in the file system or for this particular file, and so you increase the version number because you're going to have a new mutator. So basically, the master increases the version number. It sends to the primary the new version number and the secondaries, and saying like, "Hey guys, we're going to start a new." We're going to start a new mutation. You guys are forming a replica group, and your replica group with this particular version number, whatever, like version number 12. Right? And the primaries and the secondary store that version number. What do they do is they store that version number. Do they store it on disk, on their disks, or in memory, or?
I don't know.
Anyone? What do we think? Okay, let's first do memory. Let's say it stores it in memory. Would that be a good design?
No.
Sorry.
You can go.
I guess it wouldn't, because if the chunk server goes down and then it comes back up, it should know what version it has.
Yeah, because otherwise you couldn't convince the primary that it has the most recent one, right? Otherwise the master couldn't pick, the chunk server with the most recent data. So it has to be on disk. So basically this version number lives on disk, both at the chunk servers and at the master, right? So when the chunk, when the master gets back, an acknowledgement from the primary and the secondary that they written the version number to disk, and that the primary actually has received the lease, then the master also writes its version number to disk and then responds to the client. Okay. So back to the client, it responds with the list of servers, primary plus the secondaries plus the version number. Okay. Then the next step, and again here we see the whole goal is to pipe a lot of data through the network, is the client actually just sends the data that it wants to write to the primary and the secondaries. And the way it actually does it is sort of an interesting way. It basically contacts the closest secondary it knows of, out of this list, and sends the data there. And that secondary, moves the data over to the next, person in the list, and then to the next server in the list. And so this way, the data is sort of pumped, from the client, to in a pipeline to all the replicas. And when the secondary receives, the first secondary receives some of the data, it immediately starts actually pushing the data to the further down the pipeline. Okay. And the reason that this design is this way is sort of basically this network interface that the client has that goes to the outside world, usually used as a full network interface to push the data down the pipeline. And so that gives us high throughput. Okay. Okay, so then, if this is all successful and the data has been pushed, to all the servers, those servers don't store that information on disk yet, it just sits there, sort of on the side, to be used in the next step. And so the next step is then basically for the client to send a message, like an append message, to the primary. And at that point, the primary will check, the version number, right? Whether the actual version number corresponds to its version number. And if it doesn't, correspond to each, they don't match, then the primary won't allow it. The primary checks its lease, if the lease is valid. Because if the lease is not valid anymore, it cannot accept any mutation operations, because if its lease is not valid, there might be another primary outside in the world. So it checks the lease. And then if basically the version numbers match, the lease is still valid, it basically picks an offset to write at. And then the next step is basically to write the data that just came in, this record, to stable storage. So the primary actually at this point writes it to stable storage, the data, and then sends messages to the secondaries saying, please write the data to. And since the primary picks the offsets, it tells the secondaries where to write that particular record into the file. So maybe like whatever, it picks the offset 125, and then it will tell the secondaries all to write the data that came in earlier at offset 125. And then if everything works out, everybody, all the secondaries and the primary successfully write their data back to disk, then actually responds back to the client saying like, okay, success, your append actually has happened. There's a way that the write actually might be not successful, or the append might not be successful. And namely, for example, the primary is written into its own disk, but it fails to write it, it fails to connect to one of the secondaries. Maybe the secondary actually crashed, or maybe the secondary just has a network connection that doesn't work. And in that case, the primary actually returns an error to the client. So error if one secondary didn't respond. And in that case, the client library, what it will do is usually try a retry. It will reissue the same append, and we'll try again, in the hope that the second time around, that data actually that will actually get through. And so this is what they would call like you do it at least once. If you retry, will the primary pick the same offset?
I don't think so.
No, it won't. Right? Indeed, it picks a new offset, and writes it at this new particular offset. And so that means, correct, if you look at sort of the disks of the, if you have here of the file on the three replicas, the primary S1 and S2, it might be the case that we wrote like, at 125, the data, we succeeded maybe in S2, 1.2, but S2 actually doesn't has no data, correct? And then we retry again, then we might drag to read the same data to X, and maybe we'll succeed in all three. And so we can see here that basically records can be duplicated. Is this something that can happen in a standard file system, like your Linux file system on your laptop or your computer?
No.
No. Would you be surprised if your computer did this?
I mean, yeah, this is not how standard file writes work.
Yeah, and it would be inconvenient to have this property, or is it like doesn't matter?
It's inconvenient.
Yeah, inconvenient. It'd be pretty bizarre. Like, presumably, like, your compiler, produces output in a file, and then maybe, certain blocks are written twice, and then you can't run the program anymore. Right? Like, the whole thing is just garbage at that point. So it'd just be weird. Or like you write an email message, and then basically the body of the email message shows up twice. So this is not what your typical file system would do, and so this is like slightly bizarre. And what is the justification? Why do you think this is a good idea?
I'm not sure whether it's a good idea, but I'm confused how that works for MapReduce specifically. So if you run word count and you do that, and like some files, and you count, and they're like word A, it shows up once, but you do it twice because something failed, and now you have A1, so your count is going to be wrong. Yeah, I'm confused.
Yes. How do they work? It seems like, if you don't do anything, then this is really highly inconvenient, where like so returns the application will compute the wrong result.
They said they use checksums and unique IDs to check, that every every record was like by once.
Additionally, when you do record append, the response which is returned from the primary to the client gives you the offset into the file where your data was actually written, and the rest of it is assumed to be like undefined.
Yeah, I think the key point here, correct, is like basically the application doesn't interact with the file system directly. It interacts through some library, and the library basically, if you write append records, the library sticks an ID in it. And so, and also you use the library to read, these records. And so if you see a record with the same ID, you skip the second one because, it's clearly the same one. And, they have a double, an extra thing there for checksums to make sure that the record didn't get garbled. And basically to detect the changes in the bytes, but the ID basically helps them to decide or allows the library to decide, oh, well, this is the same record. I'm just not going to give it to the application. Or the application doesn't need to process it. Okay.
My question is, instead of rewriting to every replica, wouldn't it be better to remember which replica is failing and to stop until it can be written to that one?
Yeah, so there's a bunch of different designs possible. Let's return to that later. I think one reason that they do this way is like if there's a temporary failure, like a network disconnection or whatever, at least the write will succeed and it will continue. And there doesn't have to be any reconfiguration. There has to be nothing. The write can just keep going, right? And so the write doesn't have to fail. Okay.
Just a quick question in general. All of these servers are trusted, right? There's nothing else running on them. And okay.
Absolutely. This is actually an important point. This is not like your Linux file system where there's permissions and access control rights and all that kind of stuff. These servers are completely trusted. The clients are trusted. The master is trusted. The software written by Google is trusted. The whole thing is trusted. Right? This is a completely internal file system. In fact, it's sort of cool that it's sort of like a little bit maybe surprising that we even know about this file system in such an amount of detail, right? Because it's only used inside of Google. And one of the cool things is that in that period of time, and still they do, they wrote up the papers and describing actually how these systems work. And there's one reason we know about it. And that's been extremely cool that they did that. Okay. So we now understand how read works. We understand how write works. There's some sort of interesting behaviors. And I want to talk a little bit more about consistency, correct? And that really comes down to what does a read observe after you did an append. And the homework question really got at this. And so what I would like to do now is take a quick breakout, like 5 minutes, and so that you can discuss the answer to this question, and then come back and to talk a little bit more in detail about consistency. Okay. So I'm gonna make Lily. Okay. Everybody back? Everybody can hear me? Just double checking.
Yeah. Hey, Professor, a question. Can you go back to the slide with the when we talked about the right CI here? So you mentioned the master responds to the client with the version number.
Yeah.
And if that is the case, then isn't it possible? Is it even possible? Would it even have to read like a stale data, because the client has the version number and then the chunk servers would have the version number, so they can just compare those. If they don't match, the chunk servers can just say, I have a stale data, so you should not read this.
Okay, let's go. Yeah, let's go for the scenario in a little bit more detail. Let me actually get rid of this window. Okay, let's talk about so I think the scenario that we're talking about that leads into a problematic situation is as follows. We have a primary, we have a secondary, we have 2 secondaries, secondary 1, secondary 2. We have a client on this site. We have a primary, we have the client reads, gets back like a version number, say 10. Later on, another primary will okay, so S2, it gets some servers. Then at some point, and so this information is cached on the site. Maybe one of the secondaries, like S2, crashes, or at least appears to be disconnected from the network. So what the master will do is increment the version numbers. Go to 11. So messages 1111. Then another client may come along and start writing. So it will write a new value to S1 and S2 for the file. So the chunk has now been updated. So let's say the chunk was original 10, same as the version number, and now it's 11. There's 11 here. But there's the case that even though the master couldn't and the primary and the secondary couldn't talk to secondary 2, but the second client, the first client, can still talk to the secondary, and it will read their version numbers match. Right, they're both 10. And it will read, it will send 10 back. Right, so here we have a case where a write has completed, has acknowledged as to be okay, and nevertheless, there's a client that actually will read a stale value back.
So why doesn't the 11 go back to the client?
The first client. The reason is because the first client caches it for a longer period of time. They don't actually have anything in the protocol that actually does that.
So does the version increments when the system tries to push an update to S2 and it's not able to, or?
Version numbers only increment, the version numbers maintained by the master only increment when you select a new primary. Not when you do there's also a serial number that they talk about, but that's different from the version number. That's just to order, the writes. Okay.
How does a primary know which secondaries it has to check with before completing a write successfully?
The master tells it. The master tells the primary, here are the secondaries you need to update.
So when the master basically issues the lease to the primary, And if one of the secondaries is down at that moment, does the master consider this a failure, or does it just update the version number for the servers that are alive and it just forgets about the other one because it's going to have an outdated version number anyway?
Yeah, you know, the paper is a little bit vague on exactly how the recovery part or sort of the reconfiguration stuff works. But I imagine that, you know, basically the primary actually does heartbeats with P1, S1, and S2. At some point it decides, you know, S2 is dead. And then at that point, it will point, and the lease of the primary maybe runs out. And then it will create a new primary and a new S1 and another S, you know, to actually hold, you know, or maybe just S1 because there's no, you know, no additional chunk server. And that forms the new, you know, replica group for that chunk.
Oh, so the lease doesn't run out yet, basically.
Well, the primary can't point. Okay, so here's like some interesting cases. Let's see. So you guys are doing exactly the thing I want based on this paper, which is you really start thinking about all the problematic cases. And this is exactly how you think about consistency. You know, when you start thinking about consistency, you need to sort of consider all possible failures and argue whether, you know, those failures lead to inconsistencies. So the one thing, let's talk about this one case where we got a master, we got a primary, and let's say the primary and the master get disconnected. Actually, let me draw the picture slightly differently. The master in the middle, and we got a server. We got a server here, you know, S1, S2, and let's say S2 is the primary. And so, you know, whatever, it may talk to some other servers out there, and perhaps, you know, even S1 is one of the secondaries for this primary. So let's say there's a network petition. So when the master sends messages, you know, heartbeat messages, doesn't get a response. When can the master appoint a new primary?
When the lease is over for S2?
Yeah, right. Because the primary has to wait, or the master has to wait until the lease has expired. Because if the lease was not expired, then maybe we have two primaries at the same time, right? P1 and P2 are staying at the same time. And would that be bad?
Yeah, then I think, wait, would clients wouldn't know where to send to, and the master wouldn't know which one is primary, right?
Well, presumably some clients might be still talking to this primary, correct?
Yeah.
Some other clients might be talking to this primary, and they're primary for the same chunk. So I think you get very bizarre orderings, correct? Where like some rights will get lost, you know, like it would be a mess. It would be not a principled, you know, argument where like one, you know, where all rights happen in order, you know, one at a time. So this is a bad situation, and so the situation is voided, like the split brain syndrome. This is sometimes called the split brain syndrome, where you end up with a system where you have two masters, and this is a problem here is avoided because of like the lease. You know, and the master will not appoint any other primary until the lease of the first primary absolutely has expired, and it knows even if the primary is up but not reachable to it, but maybe reachable to other clients, that primary won't accept any write messages anymore because its lease has expired. Does that make sense? Okay, let me say one more thing before wrapping up, and I apologize. This is partly because, you know, I had some technical problems, but I wanted to make one more point, and it came up in the discussion too in the breakout room, which is, you know, how can you do better? You know, how to get strong consistency, or maybe just stronger. You know, they got pretty strong consistency, but not, you know, not with some little, you know, issues. And so there's a bunch of different ways you could do it. And in fact, you know, what we're going to be seeing, you know, I think one issue that shows up here all the time is like you could, instead of like updating the primary and then reporting, or making writes visible incrementally is probably not a good idea, right? So what you want to do is like update all secondaries and primaries or none. But not as in this, particular design where like some may get updated and some may not get updated, and that's actually visible to the client. And so there's a bunch of like, techniques or protocol changes that you could do that will make this better. And in fact, we'll see in labs 2 and 3, you will build systems that actually have these stronger properties and that deal with these scenarios that currently here lead to inconsistency. In fact, if you look at Google itself, and we'll read some of these papers later, Google built additional storage systems, other storage systems that have stronger consistency. And basically tailored also to a different application domain. So, for example, like in like halfway the term, we'll read this paper called Spanner, that actually has a much stronger, story for consistency and even has support for transactions. But as like the application domain is quite different. Like you can sort of see here that GFS is really tailored, to sort of the running MapReduce jobs. Okay, so I hope this is a useful introduction sort of to consistency and start thinking about these kinds of problems because they will be recurring set of problems that will show up in the rest of the term. And I apologize for running over a little bit late.
Thank you.
Hanging around. So if people want to ask additional questions, feel free to ask them. And if you have to run to another class, please run to another class.